So in order to really understand where the electrons are and what they're doing, we're going to need to understand what light is. Because light is quite a bit more complicated than you would expect. So first of all, a couple of properties of light. Let's call these the wave properties of light, because as we'll find out later, light has some other properties as well. So light, as we commonly think of it, is an electromagnetic wave. It's technically speaking, that's a perpendicular transverse wave of a magnetic component and an electric component. Not really important for you to know, except that light can be bent by both magnets and electricity. It can travel through the vacuum of space. Certain waves cannot. Certain waves, like sound, that's a mechanical wave. It needs a medium to travel through. It needs matter to travel through. But light can go through where there's no matter. Light can reflect. It can hit a surface and bounce off. Light can, that should be refract, which means it can bend as it enters a new substance it's traveling through. Light can interfere, which means it can add up with another wave and get brighter, or it can subtract with a wave and get darker. Light has brightness. That's going to be equivalent sort of to amplitude. That's how much energy is I mean, like if you turn on a light brighter, if it's the same color but it got brighter, that's brightness, amplitude that we're talking about. There's another way we can do energy as well. Wavelength, that's going to be the distance between two parts of the wave. We can go one complete cycle of the wave. Notice it goes down and it goes up again. So from crest to crest, or from here to here, or from here to here, that's wavelength. There's also frequency, and frequency is going to be measured in hertz, and hertz is a unit that basically tells us how often something happens. We can convert between wavelength and frequency with this equation here. C, that's the speed of light, because these are light waves after all. That's going to be 3 times 10 to the 8th meters per second. That's going to equal lambda, which is the wavelength, times frequency. You may see it in your book. It's the F will look like a V instead. It's not really a V. It's the Greek letter nu, but it looks like a V. So to avoid confusion, I'm going to call it F, frequency. Okay, so then what can light do for us? Well, take a look here. You may want to pause the video and look at this for a minute because there's a lot of information here. So what you should notice is that it links together different types of electromagnetic radiation to their frequency and wavelength, whether they can go through Earth's atmosphere, what objects produce them, relative size, all sorts of stuff going on here. We'll go over this in more detail in class, but certain things to notice. Visible light, light that we can see, is just a tiny part of the spectrum of things that include radio waves, X-rays, infrared, ultraviolet. As we go from left to right here, these wavelengths, these frequencies, become more dangerous to us, as we will find out as we go through this year. But all of these things are light. This was the understanding of light in the late 1800s, late 19th century. But then some things started to change. There were 2 experiments in particular that really caused waves, let's say. First of all is something called the photoelectric effect. There's certain metals that when you shine light on their surface, electrons are going to fly off the surface. And scientists were working with this and trying to come up with equations that explained how this worked, and they found something weird. It didn't matter how bright the light was that they shone on it. What mattered was the frequency of the light. With more frequency, more electrons popped off the surface, with more speed to them. So the wave nature of light didn't explain that. Another experiment was involving emission spectra. We talked about this a little bit in class. Certain certain elements, or all elements really, when you put energy into them, are going to release light. And if you take that light and break it up with a prism, it's going to break up into distinct bands. Hydrogen, sodium, helium, neon, mercury. These characteristic bands will help you to identify what element it is. The wave nature of light couldn't explain that either, because it wasn't continuous. There were very distinct bands. So what was going on? Well, that was left to two fairly smart guys to explain. First guy is this guy here, Max Planck. Maybe that should be pronounced Planck, but I usually pronounce it Planck. He was working around 1900 with more of a theoretical problem. And he said, well, what if, just like we talked about with atoms, remember Democritus's atoms were just a way of coming up with an indivisible length that we could work with? He said, what if energy is the same way? Energy isn't continuous, but it comes in certain packets. There's a certain lower level of energy that you can have. And I'm going to call these quantum. It's the minimum amount of energy that can be gained or lost by an object. And it worked for his theoretical calculations that he was doing. Now, fast forward a few years to Einstein. In 1905, he comes out with 4 groundbreaking papers, one of them being that light itself comes in packets. Light itself comes in these little packets of energy. It's basically a wave of particles. It has particle properties and wave properties. He said, let's call these particles photons. And this is the one thing that Einstein won the Nobel Prize for, explaining the photoelectric effect. Since with more frequencies, these little particles of light, these little photons, have more energy, those are going to knock off the electrons. Photoelectric effect can be tricky. I encourage you to look it up in your book, chapter 4. We'll also do some activities in class next time to simulate this. Okay, so if light comes in these small little particles called packets, what does this have to do with atoms? Well, we're almost there. The energy of a photon is related to the frequency of the light through this equation here. This is called, I've heard it called the Planck equation before. E, so that's the energy is measured in a unit called joules, is going to be equal to h times the frequency of light. H here is something called Planck's constant, which is this number here. So is this going to be big or small? Well, it's going to depend on what the F value is, right? So let's try one. Green light has a frequency of 6.2 times 10 to the 14th hertz. What is the energy of 1 photon of green light? Go ahead and pause the video and work on that. When you come back, we'll have the answer. And we're back. The answer is going to be 4.1 times 10 to the negative 19th joules. It's a very small amount, but after all, this is just a photon. It's the sort of energy that we measure electrons in. This is a very, very small amount of energy. Okay, we're almost to how this relates to an atom. So, we knew from Rutherford's model that the electrons were somewhere out there. So combining these two ideas together, some scientists figured out that electrons must have certain allowed energy states. They couldn't just be anywhere. The further closer or further from the nucleus they were, determined their energy state. The lowest energy state that electron could be in is its ground state. It can move up to a higher state, and that's called an excited state. If somehow these electrons gain energy, they'll jump up to a higher state. And that's great, but they can't stay up there forever. They're going to have to fall back down. When they fall back down, they can only go to the certain allowed energy states. Certain allowed energy states, certain amount of energy will release a certain photon. and that photon will have a certain color associated with it, giving rise to those characteristic bands of emission spectrum that we saw earlier. So, almost there then, that gives us our new model of the atom, the Bohr model of the atom. This model of the atom came out in about 1913. You've got the nucleus in the middle, you've got the electrons going around at certain allowed orbits, not just anywhere where they want. So you can see here we've got energy level 1, energy level 2, energy level 3. Electrons can move up or down. When they move up, that's absorption. They absorb energy. So let's say an electron went from energy level 2 to 3. Now it's up here and excited, but it has to fall back down. When it falls back down, that energy has to go somewhere. It's released as a photon. The energy difference from here to here will be the energy of the photon that is released. And it's great. The Bohr model explained a lot, but not everything. Because technically speaking, the Bohr model was only able to explain that pattern of bands from hydrogen. It worked really well for hydrogen, but not really for the other stuff. And not really explained how chemistry really worked. For that, we're going to have to add in some extra things. We're going to have to get into really weird stuff. But for now, we'll just stick with this explanation because it is going to explain a lot of what we're seeing. We'll do some experiments with this tomorrow. We'll do a lab the class after that where you'll have to identify elements from their characteristic light bands. So again, you should be reading the book. This is chapter 4 of the book. It will help if you both watch these videos and read the book. And if you need more resources, please come and see me. See you next time.